100, you've got like, a half a kilogram mass, that might be one of them, okay? So the only thing that's going to change in this column is you're going to take these numbers that you have for your mass in grams and multiply it by 9.8 meters per second squared, and that's going to get you your weight, and then you're going to measure how far it stretches. Good with this? Okay. Now, then you're going to graph this thing. Now, when you graph it, will this graph go through the point 0, 0?
Yes.
Yes, why?
Because if you have no weight on it, it's not going to elongate any.
Because Mother Nature is a lazy thing to
Yeah.
right? So if I don't have anything, if I have no force applied to it, hey, guess what? Oh, there's no elongation. So what are you going to put on the x-axis? Are you going to put force, or are you going to put elongation?
Force.
Force. Why?
Because it's what you're changing.
That's what you control, right? So you're going to have force here in newtons. And then you're going to have elongation here in...
Centimeters or...
No, you want to do it in meters. Okay,
Meters?
this is all about the MKS system. Okay, you want meters. Okay, you want meters. So let's say that elongation was 2 centimeters. Okay, again, I'm not trying to insult anyone's intelligence, but I do want to make sure everybody does this. There's 100 centimeters in a meter, which is going to be 0.02 meters. So I'd have that as one of my data points. So you're going to plot these points. Now, here's what's going to be most important when you plot these points. These should be pretty linear, okay? And on the instructions, listen to me on the instructions. I specifically tell you, your lab again, here, that down here on number 3, I tell you to draw a line of best fit, and then circle 2 points, and then calculate the slope. So here's what you want to focus on as you begin to do this. You all are used to calculating slope, a bunch of numbers into a calculator, and you get a number, and boom, you're done, okay? In physics, and how I view this, you all have to focus more on the process and not the product, okay? I want to see how you got that slope. And here's the reason why, okay? Adeline's groups, she's going to have a different spring than Ryan's groups is, okay? So the slope's going to be a little bit different. I don't have an answer key. I can't tell you, oh, here's this spring, and I know this spring should end up with this value. I don't know that. I don't know how you're going to draw, what points you're going to pick for your line of best fit. There's going to be some variance on this. So the only thing that I can grade is your process. So let me make sure everybody's cool with the line of best fit. So you got these data points. Basically, the line of best fit is going to split the average between these points. So you're going to take a ruler. You have to draw this with a ruler, okay? And you're going to come in here and you're going to draw something like this, okay? Where it's going to kind of split the points. On the instructions, and yes, read the instructions, I tell you I want points circled on here so that when I go to look at this, I can know exactly what your points were. Now, keep in mind the end game on this. You're going to scan this image and you're going to send it to me. So when you're drawing this graph, number one, you've got an entire sheet of graph paper, okay? I don't want a little postage size stamp up here. Number one, it's going to just irritate me to no end because the tree has already died, okay? Have the tree not have died in vain. Don't draw a tiny little graph up here. Make this take up as much space as you can because these 54-year-old eyes have seen a lot, and I'm not going to try and stare at a little tiny graph and guess what it is. Okay, you want to use as much as you can. And don't go all the way to like the bottom edge of this. Draw lines like here and here, so that way, because remember, you're going to be taking pictures of this and sending it to me. So we're going to lose something in that process. So you want to write very neatly. You want to write in a dark lead so that I can see what's going to be happening. So you're going to circle these points, maybe this point and maybe that point, and you're going to say, okay, hey, that's so many newtons and so many meters, and then that's going to be so many newtons and so many meters. Everybody's data is going to be a little bit different. Okay, that's why you have to have that. Now, and I tell you on number 3, I want to see the calculation of the slope. I want to see the process. I'm not worried about the product. I want to see the process. So what I want to see is, because remember, slope is change in y over change in x, right? Delta y over delta x. So I'm going to have like maybe 0.02 or 0.04 meters minus 0.01 meters divided by maybe, I don't know, 6 newtons minus 2 newtons, okay? Whatever that is. I want to see the units that go with this. Because if all I see is 0.04 minus 0.01 and 6 minus 2, I don't know what those numbers represent. I don't know if you graphed it correctly. I don't know if you're doing your slope calculation right. I don't know. I want to see the units that go with this. And here's the reason why. So when you get done, I want to have units of the slope, or the numeric value of the slope, and the correct units of meters per meter. Because what you'll see in physics is that you don't know what the slope represents unless you know the units that that slope has. So this is going to end up in meters per newton. So what that means is that this is how far it stretches per 1 newton of force that I apply. So there's 3 things that I don't like. Well, there's a whole list of them. There's 3 things that we'll talk about. And all 3 of them start with FR. Freshman, which I abhor, for the most part. Frizzies, like if you pull a paper out of the spiral notebook and there's frizzies on the side, okay, not a fan of those. And I don't like fractions either. So when you calculate the slope, do not leave this as a fraction. And I know the math people will tell you, oh, that's a more precise way of looking at it. No. Here's the reason why I don't want this as a fraction. I can't measure a fraction on a meter stick. I can measure a decimal on a meter stick, but I can't measure a fraction on a meter stick. So you're going to divide this out. You don't have to write down what you get out of this subtraction here. Okay, I don't need to see that step. But I do want to see this step and then just that final answer of what you're going to get here. Probably something around like 0.02 roughly. That's about typically what these springs end up, is something around 0.02. Everybody's numbers are going to be different. This is why I can only grade you on the process and not the product. Okay, so you can either show it on this paper, on the area number 3, or you can write it out on the graph itself when you're doing that. Okay? Good with this. Now, plan again for the rest of the measures.
Oh, it is actually.
Okay, well, I'll just take that. How cool is that? Wow, I wish I would have thought of that. Okay. Now, what you're going to do on number 10 on the back side is that you guys are going to draw a second graph. So if you talk to my honors physics class, they just have to draw the one graph. You guys have to actually draw 2 graphs. So on this one, we're going to switch it up. And later on, you'll see why this works in terms of energy. But on the second graph, you're going to put force on this axis, and you're going to put elongation on this axis. Now, I tell you again, what you're going to find here is a spring constant. So you're going to have the slope, draw the line of best fit, find that value. Now, when you get to number 11, let me point out exactly what I want on number 11. So on number 11, I want to find the area underneath this graph, okay? So I'm trying. But the x-axis is going to be your last elongation. So what you're going to do is you're going to come up here and you're going to find that last elongation, whatever that distance is. Then you're going to come over here and you're going to go up from that last elongation and then you're gonna see where it crosses your line of best fit, okay? I don't want the data point that corresponds with it. I want it where that line crosses that point of best fit. So you're gonna come out here, you're gonna find your last elongation, whatever that is, come up, find it where it crosses the line of best fit, and this is gonna be the height. So quick refresher, how do you find the area of a triangle? 1/2 base times height, right? So your base is going to be what that last elongation, and the height is going to be where it crosses that line of best fit. And then you're going to find that. Pay attention to the units. Oh, right, I've got a base. Oh, that base is going to be in meters. I've got a height, which is going to be in newtons. Pay attention to the units. Okay. So, we've got about 35 minutes left. As you go through this in terms of the calculations, remember, everybody's is going to be a little bit different. So what you should have, let me kind of recap everything. You should have the dimensional analysis homework, okay? That goes with the dimensional analysis YouTube video that I sent out. That's going to be due on Monday, okay? So watch that. It'll make sense when you all get to that. If you all have any questions on that dimensional analysis worksheet, save that for Monday, and I'll go over it in class on Monday. This lab is going to be due on Monday. So when you all are filling out your time log for tomorrow, I kind of estimated lecture's going to take about 50 minutes, I think, and then I put the homework down. It's about 40. That's how you're going to get your 90 minutes. Okay. Now, if your homework takes you longer than that, hey, fine. Okay. If it takes you less time than that, that's cool too. But just put down for that what I have for the lecture and then what you're going to have for the homework. Tomorrow, how you're going to get that time is you're going to watch the video and you're going to do that homework. Today's time, you don't have to worry about that because we're in class. So on Monday, you all are going to be back. But then on Tuesday, this is where you all have to make a decision. So on Tuesday, you can either decide to zoom in and actually watch me teach on Tuesday, or you can wait when I get done with that lecture, then I'm going to post that out on YouTube. So I don't care how that plays out, okay? But we'll talk more about that on Monday, but that's something if you want to begin to plan ahead, it's like, okay, hey, what's my Tuesday going to look like and what's my Friday going to look like on days when I'm into this normal routine of actually teaching. This just worked out odd that I'm going to do the same lecture with you guys that I am going to do with them. After today, that's probably not going to happen again. So that's one of the things that you need to decide as big people, how do I want to make that happen? With your CAM scanner, when you're sending me your pictures, I can't remember if I told you all, but I'm telling you again, send that in with your school email and your personal email. Okay, I've talked this 3 times today, and I can't remember if I told you guys, because you get a little bit punchy at the end of the day, breathing through the mask. So make sure that when you're sending that, attach that with your school email, okay? Because otherwise, it's just a pain for me. So when you're doing this and you're writing out these answers, make sure that you keep in mind the end product. End product is going to be, wow, Burkamp has to look at this on an iPad as a PDF file. So write neatly, write big, make it easy for me to visually grade these papers if you would. That would be amazing. Okay, so there I've got 5 stations set up out there, and there is 10 of you. Okay, so by math, that's 5 groups of 2. Physics is kind of a hands-on thing. There are going to be labs where you just have to work as like groups of 4 or 5 because you've got to like measure stuff and all that. But 5 groups of 2, and if you have any questions at all, if you're doing it right, if you're doing it wrong, ask me, and I will tell you, because it's easier for me to grade papers that are right and papers that are wrong. So on Monday, we'll go over the dimensional analysis sheet, and then we'll also go over this lab. So if you've got it done, you want to scan them and go ahead and send me. I don't recommend it because we're going to go over them in class. That way, if you have any questions, I can say, hey, you could say, wow, I had that completely wrong, okay? and then you can scan it and send it to me. Okay, are we good? Okay, fantastic. Go do science. Yep.
Are sig figs going to be important on this lab?
They won't be on this lab, because we haven't covered them yet.
Okay.
We'll deal with some things right now. Here you go, I'm gonna move you back here. So you can kind of see what's gonna happen with the lab. Okay, so. I'm just gonna let this run for a little bit so we can kind of see what's gonna happen. Then, Diego, I'm gonna trust these guys to get you your data. So when these guys get done, I'll send that to you. So, don't screw this up. Even though you haven't met Diego, Diego's watching this online and he's gonna get your data.
So we have our spring. So for elongation, I would recommend that like we measure the spring first and then subtract the difference.
It just makes sense.
Alright.
So we're using centimeters because we're going to convert.
Right, I'm gonna go get my notebook so I can write down anything extra. Alright.
So do we want to do it from the start of the coil?
That's a good question.
I'd say from the coil.
Yeah, I guess we
Don't
can
include
coil
the hooks.
and not include the hooks, but we'll have to remember that during the elongation.
Yeah. That is 12 centimeters.
Alright. 12 centimeters for the initial width.
Yeah.
Yeah. Here, you can just slip off.
Oh, yeah, okay.
Alright.
That's that.
So we got that.
So we already know the result of.
But I guess we want to try our
Yeah, we
spring
wanna-
just in case,
we wanna-
because our spring might be a little bit different.
Oh, we don't know the elongation. Mass and the forces.
0.2 kilograms.
Yeah. I believe you might want to check that. Because 200 grams to 1,000 grams.
It's about.
And then, yeah, about 14 centimeters.
Alright, 14 centimeters.
Centimeters?
14,
So
but then we have
that's
to convert that.
that's 2 centimeters, which would be 0.2 meters, I believe.
Makes 1 I have
You have a conversion table?
because 1 meter is 100 centimeters is 1 meter. Here, what you could do is you could just. So what'd you say it was 12?
Yeah, 12.
Yeah,
12 was the
divided by
initial.
100, yeah, 0.12. So 0.
Well, no. 12
Oh, 12
was
is
our
the
initial. The elongation is 2. It's
Oh,
2
2,
centimeters.
alright, so 0.02.
0.02. So then 400.
400, which would be 0.4 kilograms.
We have an elongation. About
Let's see, that goes all the way to almost 16 and a half.
yeah, it's like 16 and a half.
Alright, so 16 and a half. 4.5. 4.5 centimeters, so 0.045.
0.045. Okay. And then we can do the force calculations after.
Once we get all that.
Okay, so that's that.
Trust me. No, I can do it.
Half a kilo.
11.5.
So half a kilo is
50.
0.5.
0.5. That's inches. And that's about 17 and a half.
5.5. So 0.055.
And then a full kilo.
Absolutely, like even your voice. Worked out like what I want, I was like.
Just say 53, Josh.
Wait,
Oh, wait, we need
got
one
one
more.
more. So is there anything heavier than a kilo?
Yeah, seriously, it was just like.
1.5 kilo?
1.5 kilo. Is that too much for the spring?
We'll find out. If it is, then I guess.
I'd rather not wear out the springs.
I guess we can just ask for stuff. The springs can handle one.
I can see that, but what we're calling. Not sure, sorry. About 1.5 might be, 1.5. So anyway, so. She's the complex lab.
1 kilo.
No, he said that to her. And so then we.
That's a fair bit of elongation.
That is, 1.5 is gonna be really elongated.
Yeah. That's like nearly.
So that's just, yeah, one.
Oh, hold on. That is like. It's a little bit of an awkward measuring situation here. Like 22 and a half?
22 and a half. 10.5, 0.107.
Okay. And then 1.5 kilos, which is 1.5. So this is going to be some elongation.
The 12.7.
Prepare for elongation. Yep.
That is maximum. Oh, we gotta wait for it.
Yeah, we gotta wait for it to
calm
stop
down.
springing. Yeah, it's just
It's
bouncing.
just, yeah. That's interesting. Is it gonna stop?
There's a lot of variables.
I guess we try to stabilize. Yeah, that's better. We can probably make a measurement.
Alright,
Yeah, we can make a measurement like that. Oh, it's gonna. Is it gonna exceed the? Oh, it's just barely. Just barely.
Yeah, like 29 centimeters.
Nine.
No, 28.
28 and a half. All right. 16.5 centimeters. So 0.165 meters.
Dang. That's the elongation. Now on to force. I have the force equation in my notebook.
It's all, if you flip the lab over, it's also on the front of the lab.
Fg equals mass times 1.8 meters per second
Yes.
squared. So we'll just multiply each one of our
Masses.
masses by.
Yeah.
So I guess I can just do it with a calculator.
Alright.
Yeah, you can just.
So now I gotta consider supercomputers.
I gotta calculate.
Do you want to read that to me?
0.2
Now that we
times 1.96.
For the first one, yeah.
Oh, wait.
That's what I had.
10.8 was not.
Oh, wait, it worked out perfectly?
Yeah, basically.
How about that?
You don't have to put the units because it's already there. You don't have to put the units in the columns. They're already there.
I mean, I guess I'll just put up just.
Yeah. Diego, I'm gonna take a picture of their data and I'll just send that to you.